Hello and welcome to physics lesson 3.01 titled Vectors and Components. For the first 3 to 4 lessons in this chapter, we are going to look at how do we handle uh, vectors mathematically. There's a much different approach to doing this than there would be for non-vector math. So we're basically doing vector math. That means that the physics concepts and the labs will come later in the chapter. To start off with, we need to let's do a quick refresher on vectors. So we know that vectors are anything that have any value. A vector is defined as it has a magnitude and a direction. By the way, let me say for this video, I'm going to start off with plain paper and then I'm going to lift it and I have graph paper underneath because we're going to start off again. This is great to start with, but then we're going to want to look at some things graphically. So I've drawn a vector here and I'm going to title this vector A. So vector A, and it has a value, a magnitude of 5 units. And I'm just going to put 5 because this unit could be anything. Remember, the vector values that we've talked about so far are displacement, velocity, and acceleration. Speed, time, distance, those are all scalar values. But when we talk about displacement, velocity, and acceleration, we have to have both a magnitude and our direction here. I'm going to give myself a little horizontal. So a lot of times we'll talk about dropping in a horizontal. And what that means is a horizontal to the vector. And that's usually going to be on the what we would usually call the x-axis. This is roughly 37 degrees. Well, you might be thinking, what's the big deal? We've been adding velocity and subtracting velocity and doing this for quite a while. But here's the deal. When we were looking at velocity and acceleration, we started off in the horizontal and we would add a vector going this way, and then we'd have a vector going this way, and then a vector going this way. And we saw that the displacement was, so this was my start and this was my finish. And in this case, my displacement would have been 0 because my start and my finish were at the same point. Well, this is fine because these vectors are parallel. And as it turns out, these are actually parallel. This is called anti-parallel. Oops, not parallel, parallel. Parallel and anti-parallel. Parallel and anti-parallel vectors can be directly added. So we haven't really thought about it too much because everything we've done has been parallel and anti-parallel. But if I take this vector and I want to add it to, I'm just going to sketch something over here because I don't want a bunch of vectors on my page. But let's say I want to add that vector to this vector. There's nothing parallel or anti-parallel about it. And let's say that this has a, what does that look like? 20 degree with the x-axis. How in the world do I handle that? Well, before we can talk about motion that has 2 dimensions, and actually motion has 3 dimensions. It's got an x, a y, and a z. So, we have left, we can go, you look at a cube, you have length times width times height. So if you're going to talk about real motion and real orientation, you have to have 3 dimensions. Luckily for us, in a high school algebra-based physics class, we're only going to talk about 2. Well, it turns out we have a little trick. I can take this vector and I can break it down into pieces. And I can take this vector and I can break it down into pieces. And then we can add the pieces and reassemble them to get an answer. The pieces are called components. So components. Components are the horizontal and vertical pieces, I guess you could say, of a vector. So this vector A has components. If this was vector B, it has components. Well, let's start off and make sure that we know the anatomy of a vector. A vector has two ends. So this end is called the tail, and this end is called the head. And you have to draw vectors in a very specific way. So we always have to make sure that the components start at the tail and end at the head. So, oops, I forgot. Oh, there. I don't know if I can squeeze this in or not. I better put it up here. Components must start at the tail and end at the head. So I'm going to bring this vector down to give myself some more space. I'm going to try to redraw it the best I can. It's 5 units long, 37 degrees. All right, what I'm going to show you now is how to draw in the components of a vector. All right, I paused it because I was looking for my ruler, which is nowhere to be found, so I made myself a quickie ruler. So when drawing components, you must start at the tail. And on this one, I'm going to draw in my horizontal first. So we're going to draw in the horizontal. So I'm going to draw a line starting at the tail, and then I need the head for my horizontal. And then I'm going to go the head of the second up to the head of the resultant. The cumulative vector is called the resultant vector. So these are components. In black, I have components. And the one that I was working on is called my resultant. In a math class, we might call it a sum. Does that mean I have to go horizontal to vertical? No. If you draw in, and I'm going to do this with a dotted line, I'm going to pick a different color. I could go vertical first. I could do that, and that's okay. But you have to start at the tail and end at the head. Well, in order to be effective, I have to be able to find my components, and this is where trig comes in. And I've been talking to you guys about the fact we're going to need to do trig. So remember SOHCAHTOA. My hypotenuse is 5. This is my adjacent, and this is my opposite. So if I want to find out what my components are here, if I take the sine of 37 degrees, that's going to be the opposite over my hypotenuse, which is 5. And if I want this one, I can take the cosine of 37 degrees, and it's going to be equal to the adjacent over 5. And when I solve, I find out that this is, where am I at here? 4 units, and this is 3 units. Well, even components have to have So we're talking over here about components. Even components must have a magnitude and direction. So what we do for components is I didn't give myself a coordinate system to start with, but let's say this is positive and that's positive. So I could write vector A as a couple of different ways. I could say vector A is 5 units at 37 degrees north of east. Or I could say vector A, and I'm going to use brackets, is +4, +3. These are the same thing. What I'm saying is if I take a vector along my horizontal axis for 4, and I take a vector along my vertical for a +3, the resultant of this is going to be equal to A. These are the same thing. The way that it usually gets written in physics classes is with something called unit vector notation. Or IJK. We use an I with an arrow over the top, a J over the arrow top, and a K over the arrow over the top. And I prefer IJK notation. So the way that I would write this if I was writing it in component form is I would say +4I, +3J hat, I hat, J hat. And this is actually what you'll see me doing quite a bit. With both of these, the horizontal always comes first. And the vertical comes second. The only thing we're going to do is we're going to change this and we're going to talk about this being a velocity value or a displacement value. Or sometimes we'll just say it's just, unitless. But trig to break it down. So let me do a summary of this page before we move on to the next. So here we go. I have the anatomy of a vector. I have a tail and I have a head. When they're parallel and anti-parallel, we can add them directly. But in this case, we're getting into vectors that aren't. And so we have to learn how to break into components. And what I see that I missed there is when we break it into components, it's called resolving. So if you resolve a vector, you're breaking it into its components. Probably should have drawn it that way. So we resolved this vector that had 5 units and a 37-degree north of east angle as a +4, +3 vector. We could write it with bracket notation or with IJK notation. So what's the K? The K is if you add another dimension. We're always just going to do I and J, no 3 dimensions for us. The horizontal is always first and the vertical second. All right, I'm going to pull this away now so we can look at the graph paper underneath. And I now have on graph paper vector A, and we're going to call this vector B. So my question to you is, are vector A and vector B the same vector? Let's make this 0. Let's give these units of 1, 1, 2, 3, 4, 5, 6, 7, 8, 8, 2, 3, 4, 5, 6, 7. So we'll make the blocks one unit apiece. So are these the same vector? Tell me what you think. The answer is they are. Some of you said, no, they're not the same vector because this guy starts at -2. Let's see, I'm sorry, we're going to go, it would be a +2, -2, and it ends at 6, +1. And this guy starts at 2, 2, and ends at other coordinates. The coordinates aren't the same, but with vectors that doesn't matter. So we have different coordinates. A and B have different coordinates. But they are the same vector. Now, I don't have an angle here, but that's okay because now I'm on graph paper and so I can count blocks. So this is 1, 2, 3, 4 in the horizontal. So this is going to be positive 4i. And I'm 1, 2, 3 in the vertical. Likewise, here I'm going to go 1, 2, 3, 4. And here I go 1, 2, 3. These are the exact same vector. Coordinates don't matter. Starting coordinates are irrelevant. That's a B. We usually start working with vectors on graph paper because to resolve them, all you have to do is count blocks. You don't have to do trig. And so what we're going to do is after this, we're going to look at how do we add these graphically? And then we're going to say, how do we add these algebraically? So we'll take them off the graph paper. I think the first assignment, 3.01, has you resolving vectors and has you writing them in unit vector notation. That might come a little bit later in 3.02. But this should get your feet on the ground and get you started with your vector math. Thanks for watching and have a great day.